Alright, now that we have the primary parameters of the transmission line arranged like this, it's time for the secondary parameters. And we have two. That is the characteristic impedance and the propagation constant. Now, let me just tell the formulas of both of these. So, the characteristic impedance can be described as the geometric mean of both impedances. Alright? The geometric mean is the square root of the first number times the square root of the second number, and that is that. But, instead of Z2, we have Y2. And remember, Y2 is, remember Z2 equals the reciprocal of Y2. So instead, this is square root of Z1 over Y2. Alright? And now, we have Z1, we have Y2. So, we just put everything together. I'm just gonna put it right here now. So it's R plus J omega L over G plus J omega C. That is the characteristic impedance. Now, let's go look at the units. Now, something I have neglected to mention in the past video is that the unit for these impedances is actually ohms per meter. Why ohms per meter? Because this is just one section of a transmission line. In reality, a transmission line is very long and it has all these properties running through it. So there's a lot of them running through the transmission line up all the way to the load. And actually, if we want to simulate a transmission line, we have to think about it in terms of it having infinite length. And that's a bit different because we always have load. Right? Infinite length doesn't exist anywhere in real life, so yeah. So it has units of ohms per meter. But let's see. What is the unit of I forgot. Since this is admittance, this is inverse ohms per meter. You might call it mhos per meter, which looks like some sort of symbol that's used in a show that I watched. Or you can just have 1 over ohm meter. Alright. The units for this, let's discuss. Alright. So it's the square root of, on the top, it's ohms per meter. On the bottom, it's 1 per ohm meter. Let's multiply both the numerator and the denominator by ohm meter. On the top, we get ohm squared, and the meters cancel each other out. And this cancels everything out. So we're just left with a square root of ohm squared. And that is just ohm. So, from here, there is distance. But in the characteristic impedance, there is no distance. So that's very good. It means that when we're looking at the characteristic impedance, which will be useful in determining the reflection stuff later on, we don't need to know about distance. This is independent of distance, and actually it's also independent of frequency. The omegas here cancel each other out or something. I haven't read that far yet. But they are independent both of frequency and of distance. Now, for the propagation constant. This is given as Z1 over Z2. Alright? But since Z2 is 1 over Y2, we can rearrange it to form Z1 times Y2. So it's like the geometric mean again. So let's just rearrange it here. We get R plus J omega L times G plus J omega C. Alright. Now, the unit for this is unitless, right? This is ohms per meter. This is also ohms per meter since it is just impedance. And if you take the units, well, they cancel each other out. So it's unitless, right? hang on. It's not unitless. It's a bit weird because this is admittance per meter, but when you take the Z1Y2, it's not actually unitless. My bad. This is ohms per meter, and this is 1 over ohm meter. We can cancel the ohms, but not the meters. So we end up with 1 per meter squared and square root, so it's just 1 per meter, which is inverse lengths. It's a bit weird, but it will factor in how we use that later. Alright, so it's not unitless, only the top is unitless, I guess. Alright, so the propagation constant can be broken down into two parts, alpha plus j beta. Alright, j is again square root of -1, or the imaginary unit. This is a complex number. Alpha is the attenuation constant. It tells us how a certain thing, how a certain signal actually attenuates over length, right? Since its unit is per meter or inverse meters, this unit should be inverse meters. But what is the one doing? How can we have that? Remember that decibel and whatnot is usually unitless, right? We call it a unit, but in reality, it's unitless. Look, 20 log A, which is usually the formula for the decibel gain. All of this is unitless, maybe except for 20 and it's decibels, but usually it's just unitless. Decibel is just a fancy way of saying logarithmic gain, right? So in the same way, alpha is also logarithmic gain, but it is just in nepers. The unit of alpha is usually in nepers, wherein 1 nepper per meter is 20 log E decibels per meter. So that is the attenuation constant. Alright. So when we encounter this and then we see alpha equaling 1 nepper per meter, we're actually seeing 20 log E per decibels per meter of attenuation. 20 log E is around 8.686 decibels. There we go. All right. Next is beta, or the phase shift constant. The phase shift constant is how much the phase changes over the distances. So the phase shift constant is in radians, which is typically considered unitless, over meter. So radians per meter. It basically tells us how many radians per meter it is moving. And actually, the beta here, its unit is radians. If you want degrees, just know that pi radians is 180 degrees. There we go. That is the secondary parameters for a transmission line.